This is question 1 on midterm 2. Question says, a solid spherical conductive ball of radius r1 is placed inside a conductive spherical shell of inner radius r2. There's a voltage difference of V12 measured between the inner and outer inner sphere and outer shell. We have to find the capacitance in terms of the given quantities, which was R1, R2, and V12. So since our equation that we're supposed to be using is C equals Q over V, and in this case V is that constant V12, and we have to essentially find Q, find how charge relates to that potential difference, and radii, which is the terms we were given. So we can use the equation for the potential difference of a surface, of a surface is equal to negative of the integral the electric field times, or dotted with dr. That's for spherical symmetry. And then along with that, we can find how that electric field from the potential difference is related to Q, which is from Gauss's law. So first thing we have to do is use Gauss's law to find the electric field between R1 and R2. So we can find dA, which in this case, since this is a sphere, dA will be 4 pi r squared. So we can plug that in for our equation and then set that equal to the Q enclosed over epsilon naught. And we solve that, and we know that due to it being a sphere and uniformly, the charge uniformly distributed, it'll be in the radial direction, which is that r hat there. And then for this Gaussian surface, or Gaussian radius between R1 and R2 here, this is what we're looking for based in the question. That's where the potential difference is. We can say that the charge enclosed will be positive Q because of that accumulated positive charge that is uniform to this accumulated negative charge. And then, or you can just use the electric field of a point charge, and that works as well. And then for the second part, you need to plug in your electric field that you got from Gauss's law into the equation for the potential difference. And so for that, it'll be equal to negative the integral from R2 to R1, because the potential difference is decreasing as R increases. So that'll be equal to your electric field dotted with dr, and since they're in the same direction, since dr and electric field are both in the radial direction, it'll just be the magnitude of the products of the electric field and dr. So we can take out the constants, and we see that it's the Q over 4 pi epsilon naught times the integral from R2 to R1 of R over R2 dotted with dr. Then we can integrate and solve for Q, which is what we need in order to solve our capacitance, So we get that V12 will be equal to negative Q over 4 pi epsilon naught times the negative 1 over R evaluated from R2 to R1. We get this equation here, and then we can just solve for Q. And our Q is in terms of V12 and R1 and R2, which is good. That's our given values. And then we can just plug in that Q into the capacitance formula, and we end up getting that the capacitance is equal to 4 pi epsilon naught over 1 over R1 minus 1 over R2. That's all you need to solve for this. And the tricky part of this question is just seeing that you need to relate variables that almost seem unrelated at first glance, such as radii and potential difference, or voltage difference. you can just work through that by understanding the relationship between electric field and potential difference and charge.